Hey everyone, welcome back to my channel. Today we're going to discuss about prime factorization and irreducible factorization. And perhaps most of you have already saw the post that I put on the community. And the first one, which was from last week when I filmed this, was asking whether prime factorization is always unique in any situation. And then for the second post, which was published yesterday, again, based on the day that I filmed this, says that is irreducible factorization always unique in any situation? So I noticed that most of you answered yes for both kinds of factorization. So today we're going to discuss whether they're true or not, okay? And to see if you guys actually got the answer correct. So most of you, actually, in fact, so far there's only one person disagree that prime factorization is always unique, and the rest of you all, well, and then there was another people who said he or she doesn't know. Okay, and everyone else thinks that prime factorization is always unique in any situation. And this part, I'm going to skip it first, and let's talk about what happened in the second post. So in the second post, we said whether irreducible factorization is always unique or not. But first, let's try to understand what is the meaning of irreducible. So in algebra, when we say something is irreducible, let's call it some variable a. Or you can just think it, in algebra, we will call it an element in any situation. So you can put it in a group or in a ring. And what does that mean? If you don't know it, it's okay. Just stay on it, and I'll find some time to try explain what those abstract ideas are. But anyway, suppose that we have an element in a ring. Then we call that element A is irreducible if and only if there is no other two elements B and C in the same ring that are not unit, such that the product of B and C, or we can simply say B times C, is equal to A for a commutative ring. And again, commutative means that the order of operation doesn't matter, meaning that B times C will just be C times B, okay? And again, when we say commutative, means that we can also, we are allowed to switch the order and it will not affect the results. So for example, addition, the regular addition and regular multiplications are considered as commutative, because we know that any two things adding together will always yield with the same results, no matter which one goes first and which one goes second. But subtraction will be different. Subtraction is not commutative because, again, we can give an example. Let's say 1 and 3. 3 minus 1 will give us 2, but 1 minus 3 will give us -2. And those two will not end up with the same result. In this case, we will call this operation not commutative. Anyway, so this is a definition of what an irreducible element means. So back to the question. Is irreducible factorization always unique? Quick answer, no. Why is that? So let's consider the following. We will have a ring called C6. And again, what's a ring? Ring is basically just saying that a mathematical set, or you can think a mathematical set is a collection that relates to math, of course, that actually has something in it, possibly. You can have nothing in it as well. But in this case, here we have the set Z6, which means the remainder part after an integer divided by 6. So again, it will just be 0, 1, 2, 3, 4, and 5. And then as a ring, it has to contain 2 different operations. What does that mean by operation? Well, operation just really means like some kind of similar to a function that can actually, after you choose something as an input, and then you play with the operation, it will get something out. So, such as addition, multiplication, something like that. So, our operation here will just be both addition and subtraction, and multiplication. Okay, and this is the ring that we have. Then let's see why irreducible factorization is not unique here. So here I'm going to make an extended ring, meaning that I'm going to use whatever we have here and then build something out from it. So this is the actual ring that we're going to use. We're going to consider the ring Z6, meaning that these elements here join with X. So we're going to make polynomials with the coefficients from 0 up to 5. Okay, and of course our operation will still be multiplication and addition. Then now we will say that we have a ring such that we can now try to pick some elements. So let's say we're going to choose this element here, 3x plus 2. All right, first, this has all the coefficients between 0 to 5. Great. And this is in fact a polynomial. Of course, we don't see any x to the negative power or x to x to like something not positive integer powers. So we can agree that this lies in the ring Z6 joint X. Then let's see how we can actually factor it. Well, clearly we can factor this out as how we usually do in high school algebra. We can just use the cross product to get x plus 1 times x plus 2. Good. But in fact, we can try to factor this out in a different way. How? So consider the definition of Z6 here is just the remainder part after we divide by an integer by 6. But at the same time, we can also try to use other integers to replace it technically, because they will just have the same what we call equivalent class, but it just means the same representation when we try to choose some other integers. For example, if we have negative or positive 6, we know that 6 is not inside of here, but if we follow the definition, 6 divided by 6 is equal to 1 with no remainder, or remainder is equal to 0. So we will say that 6 is equivalent to 0 in the ring Z6. Another example is, let's say, negative 4. Then we can just do the same game. It is not inside of here and is actually smaller. We can just add multiples of 6 until it becomes one of the elements in the ring. So in this case, we can add one copy of 6, which is going to give us positive 2. So we can just claim that negative 4 is equivalent to 2 in this particular ring. How does that help us? Well, based on what we just did, we can also say that if we have something inside of the ring, we can try to replace it with some other things too. Such as if we have a 2, we can replace it with negative 4. Or if we have 5, we can replace it with negative 1. So in this case, we can also rewrite our quadratic expression x squared plus 3x plus 2 into the following. We can write 3 as negative 3, and we will now get x squared minus 3x plus 2, which if we try to factor out as usual, we will get x minus 1 times x minus 2. But again, we can also play the same game since we're actually in this particular ring. So negative 1 is again equivalent to positive 5. We can just add 6 to get that. And x minus 2, we can rewrite it as x plus 4. And again, we just add 6 to it. So here comes the question. These two polynomials are actually equivalent in this particular ring. But when we try to factor out, we actually get two different expressions. One of them says x plus 1 times x plus 2. The other one says x plus 4 times x plus 5. So how is that possible? Well, it is possible because we're not in something what we call a field. We're now actually in a ring only. And in this example, it's shown that even with the same expression, or we start with the same element, or maybe polynomials, we can actually end up with different ways of factoring. And what does that do to the idea of irreducible factorization? Again, irreducible means that there's no other two non-unit elements to get the products of whatever we have. And in this case, we have two factors in each case. Each factor is a linear expression. We have x plus 1 or x plus 2, x plus 4 and x plus 5. Is it possible to actually factor out x plus 1 or maybe x plus 5 in our ring? No, because again, if we try to factor out one of the factors or one of the polynomials must be a unit, meaning in this case, we must get one for p of x or maybe q of x, as we try to write this as a product of the linear expression. Therefore, these linear expressions are called irreducible. But we now just see that irreducible factorization is no longer unique for some situation. Good. So now we're going to move back and talk about prime factorization. So before we talk about whether it is always unique or not, let's talk about what is actually a prime. And be careful, prime is not the same as prime number. I know most of you will actually think, well, prime factorization must be unique because we all know what primes are. In fact, whenever you say prime, I believe most of you are actually thinking of prime numbers as what we usually see, like 2, 3, 5, 7, and so on and so forth. But what is the actual definition of prime in algebra? Here is the definition. If we call an element P inside of, again, some ring here, then P is a prime. It's a prime by definition, meaning if and only if, for any elements in, let's say, any two elements here, A and B, in the ring, if the product AB is a multiple of the element P, then either A is a multiple of P, or B has to be an element, has to be a multiple of P. And again, this is very similar to how we usually think of prime numbers for natural numbers. It is the same. It's pretty much the same idea, but now instead of talking about just positive integers, we'll actually move on and try to bring it to other different concepts, such as, again, we can just use the same example in Z6. And again, Z6 are containing the 6 elements, 0, 1, 2, 3, 4, and 5. And if we consider it as a ring, then we will have the regular addition and the regular multiplication here. So in this case, we can actually get our Cayley table or multiplication table on the right hand side here. So, and again, if we look at this table here, we actually would get something such as 2 times 3 is equal to 6, which is actually equal to 0 in our situation. But we can see that 2 is a prime by definition, because if we consider all 6 elements, 0, 1, 2, 3, 4, 5. Okay. If we look at our table here, multiplication table here, only 0, 2, and 4 are multiples of 2. Meaning we can say that 2 is a factor of 0, 2, and 4. And as we try to factor out 0 and 0, 2, and 4, we get the following. We can see that 0 here could be written as 2 times 0, and then we can have, for example, 2 here can be written as 2 times 1, or other situation, 4 can be written as 2 times 2. But again, we can also get something like 0 can be written as 4 times 0. 2 can be also written as, let's see, 2 times, what can we choose? 2 times 1, we have already used it. 4 times 2. And then 4 we can rewrite as, let's see, we can pick any. 4 times 1, this is the only thing that we then use, or maybe 4 times 4. But we can see that for any number or any elements that we pick that are actually multiples of 2, if we try to factor out, at least one of the terms must be a multiple of 2 as well. Such as the first case, we have both 2 and 0 are multiples of 2. Or for the fourth case here, we have 2 can be written as 4 times 2. Or we can have, such as here, let me change it. 4 is equal to 1 times 4, but 4 is still a multiple of 2. So we should just show that 2 is actually a prime in this particular ring. But how does it change our gain? Here is the deal. Now if we consider 2 itself and raise it to the third power, meaning that we have 2 times 2 times 2. Okay, what do we get? Well, 2 times 2 in the Cayley table, or in the multiplication table, we have 2 times 2 is 4. Then what's 4 times 2? Well, from the table we have 4 times 2 is going to give us 2. So, in other words, we can rewrite 2 as 2 to the third power, okay? Or 2 is actually equal to 2 times 4 as well. Even though 2 is a prime number, it is not irreducible. And in fact, it is no longer unique because we can rewrite 2 as 2 to some higher power in this case. And again, as 2 being a prime number, both ways are actually considered as prime factorization because all the factors in the expressions are prime. But we also could see that the exponent part here, maybe I should put a 1, are actually different now. So that we cannot consider them to be unique because they don't have the same power by the definition. Therefore, the answer for the first problem is prime factorization always unique in any situation is also a no. That's it. This is pretty surprising, right? So if you have any thoughts and thoughts or some questions, you can just put your comments below, and especially about the concepts that we talk about in this video, because I know it is a little bit complicated. So don't hesitate if you have any questions. And also, if you enjoyed this video, please don't forget to like and subscribe to my channel so that you can find all more of my other videos. And don't forget to turn on the notification so that you won't miss any of my new videos either. I'll see you guys next time.